Now, so far we have looked at observatories on Earth, optical and radio. But there's a big problem: the Earth's atmosphere. So let's explore why astronomers go above the atmosphere, into space, or even into airplanes to get a clearer view of the universe. The atmosphere is both a blessing and a curse. Of course, it protects us from harmful radiation, but for astronomers, it causes trouble. First, turbulence in the air makes stars twinkle. Now, you have all seen stars twinkling at night, right? And that twinkle is actually the atmosphere blur in the light. So, astronomers call this problem seeing, and it makes images fuzzy. So, we discussed this before, remember? And the second point is the atmosphere blocks most of the electromagnetic spectrum. Only visible, some radio, and a tiny bit of infrared sneak through. Everything else, most infrared, ultraviolet, X-rays, gamma rays, get absorbed. And that means from the ground, we can't study many kinds of cosmic signals. So think about this. If the atmosphere blocks gamma rays completely, how would astronomers study violent events like supernova explosions? You would have to put a telescope in space, right? Now, when you put a telescope in space, you remove all those problems. No turbulence, no twinkling. So, the sharpness of the image is limited only by physics, the size of the telescope's mirror, and the wavelength of light, a rule called diffraction. And that means you get the clearest, most detailed pictures possible. And even better, space gives you access to the entire electromagnetic spectrum, not just the little windows we can get on the ground. So that's how astronomers can study everything from cool star forming clouds in infrared to exploding stars in X-rays to powerful gamma ray bursts. So if you are designing a telescope to study planets around the other stars, would you want it on the ground or in space? Space, right? Why? Because you would need sharp, undistorted images and access to infrared light to see atmosphere and dust. Alright, so the bottom line is the atmosphere is like a filter, sometimes helpful, sometimes frustrating. And to see the universe clearly and across all wavelengths, astronomers need telescopes in space or at least above most of the atmosphere. And that brings us to one of the most famous space telescopes of all time, the Hubble Space Telescope. Now, you have probably all seen the breathtaking images of galaxies and nebula taken from Hubble Space Telescope. But Hubble's story is also about groundbreaking science and even teamwork between engineers and astronauts. Now, this picture here, it shows Hubble orbiting Earth, almost like a satellite. But instead of communications, it's sending back views of the universe. Now, Hubble was launched in 1990 aboard the Space Shuttle Discovery. And it carries a 2.4 meter wide mirror about the size of a classroom whiteboard. So that mirror collects visible light but also near ultraviolet and near infrared. So it can see more than our eyes can. And Hubble orbits about 570 kilometers above Earth, far enough to escape the atmosphere, but is still close enough for astronauts to visit if repairs are needed. So why do you think NASA chose an orbit close enough for astronauts to reach? Because they could fix problems and upgrade instruments, which they actually did several times. So because Hubble is above the atmosphere, its images are crystal clear, no twinkling, no blurring. And it can pick out incredibly faint details like galaxies billions of light years away. or planets orbiting stars. And one of the most amazing things about Hubble is that it wasn't just left in space to drift. Astronomers actually have visited it 5 times between 1993 and 2009. They repaired broken parts, swapped out cameras, and upgraded its instruments, keeping it useful for over 3 decades. So, Hubble changed the way we see the universe. But astronomers wanted to go even further to see colder, earlier, and faint objects, especially in infrared. And that dream led to the James Webb Space Telescope. Now this illustration, it shows the James Webb Space Telescope, or we call it as JWST, during launch. So it was launched in December 2021 after decades of planning and development. And unlike Hubble's single round mirror, Webb has a giant 6.5 meter mirror made of 18 hexagonal segments coated in gold. And the mirror is made of beryllium, which is strong and light, perfect for space. So this gives JWST nearly 7 times the light collecting area of Hubble, meaning it can gather much more faint light from distant galaxies. Cool, right? Now Webb is an infrared observatory. That means it sees light that our eyes cannot. It carries both near-infrared and mid-infrared instruments. And this is important because infrared light passes through dust clouds that block visible light. That means Webb can see star nurseries where new stars and planets are being born. So to work in infrared, Webb has to stay extremely cold. And that's why it uses a tennis court size sun shield and orbits far from Earth at a special spot called L2, about 1.5 million kilometers away. So the sun shield blocks heat from the sun, Earth and Moon, so Webb can detect the faintest cosmic signals. So why do you think keeping the telescope cold is so important for infrared? Because if the telescope itself is warm, it would glow in infrared and blinds its own instruments. Now Webb's main goals are breathtaking. First, it aims to see the very first stars and galaxies that formed after the Big Bang, objects so distant their light has shifted into the infrared. Second, Webb studies exoplanets. So by analyzing the infrared light passing through an exoplanet's atmosphere, astronomers can detect gases like water vapor, methane, and maybe even signs of habitability. So Hubble gives us stunning visible light images of the universe, but Webb is now open in the infrared universe, helping us look back in time and even study the atmosphere of other worlds. Alright, now we just saw how JWST explores the universe in infrared from space. But before that, astronomers also used aircraft and earlier space telescopes to study infrared light because our atmosphere blocks most of it. And this photo shows SOFIA, the Stratospheric Observatory for Infrared Astronomy. SOFIA, the Stratospheric Observatory for Infrared Astronomy. So believe it or not, that's a 747 airplane with a telescope inside. So we will come back to this in a moment. Now infrared light is especially hard to observe from the ground. Why? First, water vapor in our atmosphere absorbs most infrared wavelengths, especially in the mid and far infrared. And second, the atmosphere itself actually glows in infrared, kind of like how the sky glows in visible light during the day. So that makes faint space objects nearly impossible to detect from Earth's surface. So imagine trying to see stars through a glowing fog. That's basically what infrared astronomers face from the ground. So what's the solution? Go above the atmosphere. and Sophia was one creative solution. It was a joint NASA and German project where engineers installed a 2.7-meter telescope into a modified Boeing 747 SP aircraft. And the telescope pointed out through a special rollback door in the fuselage. So flying at 14 km above 45,000 feet, Sophia rose above most of the water vapor, giving it across to infrared wavelengths that are blocked from the ground. And Sophia flew 921 missions before being retired in 2022. And it not only collected valuable science data but also carried science teachers and educators on board, inspiring students worldwide. Now, why do you think scientists went through the trouble of flying a telescope on a plane instead of just putting one on a mountain? What's the reason? Because even tall mountains don't get you above most water vapor in the atmosphere. So, of course, the best solution is to get completely above the atmosphere into space. So, the European Space Agency's Herschel telescope with a 3.5-meter mirror operated from 2009 to 2013, and it studied star formation, planet formation, and chemistry in interstellar clouds. And looking ahead, NASA is planning the Nancy Grace Roman Space Telescope launching around 2027. So Roman will study the large scale structure of the universe and also search for planets around the other stars using powerful infrared instruments. So whether it's an airplane carrying a telescope into the sky or spacecrafts like Herschel or Roman, infrared astronomy needs to escape the Earth's atmosphere. Now let's look at some of the results infrared observatories like Sophia and Herschel gave us. So these telescopes shows us the universe in ways our eyes can't. And here you see Jupiter in visible light, the way we would see it through a telescope. And on the right, Sophia observed Jupiter in infrared light. So notice the bright white stripe. That's where clouds are thinner. So we can see deeper, warmer layers of Jupiter's atmosphere. So infrared gives us a whole new view. So Sophia was not just a cool flying telescope. It made detailed infrared maps of planets, stars, and galaxies. And by looking at objects like Jupiter in infrared, it helped scientists to study atmospheric layers, star-forming regions, and even the center of our galaxy, which is hidden in dust when viewed in visible light. Now looking at the two Jupiter images, visible and infrared, what new information do you think infrared reveals that visible light cannot? What do you think? Deep layers, heat patterns, cloud appearancy, and so on. Next, here's an artist view of the Herschel Infrared Space Telescope. So Herschel carried a 3.5-meter mirror, the largest infrared mirror ever launched at the time. And its instruments were cooled almost to absolute zero. And that cooling was critical because any heat from the telescope itself would swamp the faint cosmic infrared signals. So Herschel focused on some of the astronomy's biggest questions: how stars and planets form, and what molecules exist in cold clouds between stars. And it even detected water and complex molecules in star-forming regions. So why do you think astronomers are so interested in studying the chemistry of interstellar clouds? Why? Because those clouds are where stars, planets, and maybe even the building blocks of life come from. Now the challenge with infrared space telescope is cooling. They carry a limited supply of liquid helium or other coolants. And once that coolant runs out, the telescope warms up and can no longer detect faint infrared light. So that's why Herschel only operated from 2009 to 2013. But in that short time, it made groundbreaking discoveries. So infrared astronomy shows us hidden worlds inside planets, star nurseries, and interstellar clouds. But what about the universe's most extreme events, like exploding stars and black holes? So for those, we need to turn to high energy space observatories, X-rays and gamma rays. Now the hottest and most energetic events in the universe, things like exploding stars, black holes and gamma ray bursts, give off ultraviolet X-ray and gamma ray radiation, which never reach the ground because our atmosphere blocks them. That means we need to go to space to observe them. Now here's an illustration of how X-ray telescopes focus light. Unlike optical or radio telescopes, X-rays just pass through mirrors unless they strike at very shallow grazing angles. So that's why these mirrors are shaped like barrels rather than simple dishes. Now we know Earth's atmosphere protects us from harmful high energy radiation. But that's bad news for astronomers. So to study the hottest phenomena in the universe, we need to put telescopes above the atmosphere in orbit as we just discussed. Now here's some example. Chandra has been in space since 1999 and studies X-rays from black holes, supernova remnants and hot gas in galaxies. So it used those barrel-shaped grazing incidence mirrors you see in this figure to focus X-rays onto detectors. Next, Fermi looks at gamma rays, detecting bursts that can release more energy in seconds than our sun emits in its entire lifetime. Alright, now with this we conclude our chapter on telescopes and observatories. So we have explored everything from ground-based optical and radio telescopes to airborne and space observatories and finally the high-energy telescopes that let us see phenomena invisible from Earth. So each type of telescopes reveals a different part of the electromagnetic spectrum, allowing us to study objects and processes invisible to the naked eye. Alright, so let's wrap up the chapter with a brief summary of the key concepts we have learned. So let's start with radiation. We learned that light is an electromagnetic wave traveling at the speed of light c. Its wavelength lambda is the distance between two peaks and frequency nu is how many waves pass per second. Now multiply them together. Lambda times nu, then you get c. Lambda nu equals to c. And light behaves like photons. And light behaves like photons, tiny packets of energy. High frequency means higher energy and also shorter wavelengths means higher energy. And the electromagnetic spectrum includes everything from gamma rays and X-rays to radio waves. But remember, Earth's atmosphere only lets through visible light, some infrared and some short radio waves. The rest is blocked, which is why space telescopes are so important. Our next topic was telescopes. There are basically two types of optical telescopes. Refracting telescopes use lenses to bend light but have color issues called chromatic aberration. And reflecting telescopes use mirrors which are easier to make large and don't have color problems. And next, telescopes are measured by light gathering power, LGP, how much light they collect. Resolving power, how finely they can see details. And magnifying power, how much bigger they make objects appear. And modern telescopes also use active optics and segmented mirrors to build huge, precise instruments. Now, where do we build observatories? On high, remote mountains to get steadier air and avoid light pollution. But radio telescopes are placed far from human noise. So telescopes must track the sky, and equatorial mounts follow Earth's rotation naturally, while alt-azimuth mounts use computers. And advanced techniques like adaptive optics correct for atmospheric turbulence. And interferometry combines multiple telescopes to act like a giant one for sharper images. Next section we learn about airborne and space observatories. So remember, Earth's atmosphere can blur images and blocks gamma rays, X-rays, UV, far infrared and microwaves. But observatories in space don't have this problem. Their resolution is limited only by diffraction, and they can observe the full electromagnetic spectrum. And some examples are Hubble, which is visible near UV and near IR, and JWST observes near and mid-infrared. Next, Sophia and Herschel focused on infrared, and Chandra and Fermi observe high energy phenomena like X-rays and gamma rays. Alright, that's the chapter summary. Now don't worry about memorizing everything. Just get the main ideas and make sure to go through the practice questions to check your understanding.